Okay, welcome to the next Physics 121 video. Um, what we talked about in the last video was Amperes Law, and Amperes Law was that if we took the line integral of a region of space with a magnetic field, so that the line integral is b dot ds, and we did that around a closed loop, what that would have to be equal to is a constant mu naught times however much current passed through that loop. And if there was no current through the loop, that line integral would evaluate to 0. But if we had some current through the loop and we make a good choice about the loop that we choose, we can actually use Amperes Law to calculate magnetic fields due to certain arrangements of currents. And today, in this video, we're going to consider two important applications. One is a solenoid, and the other is a closely related toroid. Before we do that, I just wanted to make one comment about our derivation of Amperes Law. We did it using, we were completely arbitrary about the path that we could take, so that was general, but we considered only long, straight currents. And if you thought carefully about that, you would realize that, well, not everything is a long, straight current. In fact, the solenoid that we'll look at today is not a long, straight current. And so we haven't done a completely general proof of Amperes Law. It turns out that this expression is generally true, but we're not going to pursue a complete derivation of this result for any arrangement of current. If you were to take some more advanced physics courses at UBC Okanagan, we have a Physics 301, a third-year E&M course, and Electricity and Magnetism. And if you took that course there, you will do a general proof of Amperes Law. Okay, so with that, let's consider the case of a solenoid. Okay, so what is a solenoid? Let's imagine that we had some kind of rod, like a plastic rod or whatever, and we're going to take a wire and we're going to wrap the wire around our rod like this. And so we form like it's like a slinky or a spring. And so we're going to take this coil of wire and we're going to pass a current through it. Actually, let me draw the current in the other way. So we'll send a current in this way, and it'll go around our wire, and so it's going to loop around where on the front face that we're looking at, the current is going in the upwards direction. On the back face, which we can't see, the current's going downwards. Okay. So if you think of this geometry, it's as if we've taken a bunch of loops of current and added them together. So the solenoid is equivalent to a stack of current loops. And so that's kind of useful because it's a useful way of thinking of this, because we know what a loop of current does. If we have a current in this direction, then the magnetic field due to that loop of current looks like the magnetic field of a bar magnet or like a dipole. Okay, so what I want to do is I want to think about whether or not we could say something about what the magnetic field must look like for the solenoid And then once we have that information, we'll see if we can use that to apply Amperes Law. Okay, so we have a stack of current loops, and so what I'm going to imagine is that we've got one current loop here. I'm drawing the current loop in cross-section. And so we have a current coming out of the screen at the top. It loops around and goes into the screen on the bottom. So imagine this is a cross-section of a loop. So this is a sequence of current loops in cross-section. So this is loop number 1 is over here, and then over here we've got a second loop, loop number 2, and then over here we've got our third loop. Okay, and so what I'd like to do is I'd like to see if we could figure out what the magnetic field looks like at a point inside the solenoid and a point outside the solenoid. So if you do your right-hand rule where let's curl our fingers in the direction of the current. So the current comes out of the screen at the top, goes down towards the bottom of the screen, and then goes into the screen at the bottom. So the magnetic field at the center of that loop, which is something that we've calculated, it is going from left to right. So let's say this is the magnetic field due to current loop number 2. So we're at the center of current loop number 2. So we'll call that B2. And then let's consider a point that is outside of our loop. So outside, what we would imagine is that this is like a dipole, and so the magnetic field kind of loops around something like this, and over here the magnetic field due to loop number 2 is in the opposite direction. So this is maybe B2. Okay, now let's think about, say, loop number 1. So right on the axis of this loop, the magnetic field line is going to go straight, and we'll get a B1 over here. It'll just be weaker in magnitude because we're not right at the center of the loop. We're, say, displaced to the right by a certain distance. Okay, and then if we draw a dipole type magnetic field, what would happen is this would come in and it would begin to loop around. I didn't draw that very nicely. Let's see if I can clean that up a bit. So the magnetic field comes around and it's going to form this loop. So at this point, the magnetic field is something like this, B1. Okay, and then we've got, say, B2. And so again, right on the axis, right on the center, the magnetic field of, the third loop is going to look something like that. And let's see, we're going to have, again, this kind of dipole type magnetic field that is going to be pointing out this way. So over here, we get something like, oh, sorry, that's not the best. Let's clean this up. We get something like a B3 over here. Okay, so if that figure is not very satisfactory, you can look in your textbook, and it's figure in chapter 29 is figure 29.29, and it's part B is what we've tried to reproduce here. Anyways, the main point is that inside of the solenoid, so inside the solenoid, B1 and B2 and B3 are all in the same direction, and so the result of the sum of those things inside is a net magnetic field that's fairly strong and points from left to right. On the other hand, outside of the solenoid, you can see that B1 and B3 both have X and Y components. If the Y component is vertical, then B3 has a positive Y component, B1 has a negative Y component, and those will cancel, leaving just the X components. If we add up the X components of B1 and B3, that's to the right, and that's opposed by the X component of B2, and so those approximately cancel out. So outside the solenoid, the sum of the individual magnetic fields is approximately 0. Okay, so then what we expect that if I draw my cylinder, this is like our coil former, so we're going to wrap our coil around there. Let's try to draw what we think the magnetic field would look like. And so this time I've got my current coming down in front of us. Okay, good. So let's see, by the right-hand rule, I should just make a comment here that the solenoid that I drew over here has current in the opposite sense of these coils here. So maybe if I want to make these pictures consistent, maybe what we should do is reverse the direction of the current here just to make these pictures consistent with each other. So in the problem we just thought about, current was coming out of the page at the top, and so we have current coming down and then going into the screen at the bottom. And so that means over here the current's coming up and over here the current's coming down. So at least now all of these figures are consistent. Okay, so what we've deduced then is that the magnetic field B is equal to 0 outside of our solenoid, and then inside we have a strong magnetic field that is along the axis of the solenoid. So let's draw it like this. So this is B inside, not equal to 0. Okay, good. So now let's see if we can apply Ampere's law to the situation. So let's apply Ampere's law. So again, let's draw our coils in cross-section. So we're going to have a high density of coils. Let's imagine we take this wire and we wrap it very tightly around our cylindrical former. so that when we look in cross-section, we have the loops of wire one after another. And then down here, the current is going into the screen. Okay, so here we have I coming out of the page, and at the bottom, I is going into the screen. So what we have to do is we have to choose a closed path. Let's draw our magnetic field. So these are our magnetic field lines. And out here we have B equals 0. And then we want to evaluate Amperes Law. And Amperes Law is this integral of B dot ds is equal to mu naught I through. And we have to choose a closed path. Okay, so let's make a choice for a path. Let's take a path that's going to be rectangular and something like this. And what we'll do is we'll take our path in the clockwise direction. It doesn't matter, but we have to choose a direction. I'm going to choose clockwise. And what we could do is we could imagine breaking our path into different segments. There's the first segment, which is inside the solenoid, a second segment that goes from inside to outside, a third segment that's outside, and then a fourth one that goes from outside back to inside. Okay, and then we have to evaluate B dot ds around the closed path. But that's just equal to B dot ds on part 1 plus B dot ds on part 2 plus B dot ds on part 3 plus B dot ds on part 4. Okay, maybe part 3 is the easiest one to deal with, because what we've tried to argue is that in part 3, the magnetic field is equal to 0. Right, so we said, okay, B is equal to 0 out here. Okay, so for segment 3, B is equal to 0, therefore this B dot ds for part 3 of our loop is equal to 0. Okay, so we got rid of one of them, so that's good. Let's deal with 2 and 4 now. And so if you look at segment 2, part of it is outside the solenoid where the B field is equal to 0, but part of it's inside where the magnetic field is not equal to 0. So let's think a little bit about this part that is inside. And so we have a ds vector that goes like that. And what's important is that the ds and the magnetic field are perpendicular. Okay, so for segments 2 and 4, right? Is that what they were? Yes, 2 and 4, either B is equal to 0 or B is perpendicular to ds such that B dot ds is equal to 0. Okay, because the dot product is going to involve the cosine of the angle between the vectors, and if that angle is 90 degrees, cosine of 90 is 0. So in either case, either b equals 0 or the dot product is equal 0, what we're going to get is that b dot ds is equal to 0 for either segment 2 or segment 4. Okay, so now we've gotten rid of the second and fourth terms. So all that's left is now segment 1. And in segment 1, here's our ds vector, and it's in the same direction as the magnetic field. Okay, so for segment 1, B is parallel to ds such that B dot ds is just equal to B ds, because we'll get the cosine of 0, which is 1. All right, so what we've got then is that this B dot ds for the whole closed loop is now equal to just B ds for the first segment of our red loop. Now if we look at that first segment, what we find is that no matter where I am along this path, I'm always the same distance from the currents that are either below or above. And so if that's the case, you wouldn't expect the strength of the magnetic field to be changing. So since along path 1, we're always the same distance from the current sources, or let's say the sources of current, we would expect B to be constant everywhere on that path. And so that means that this line integral that we're trying to calculate is just B, some constant, times the integral of ds along path 1. So what we have to do to go further is we have to specify how long that path is. And so let's say it has some length L. So if segment 1 has length L, then what we would say is this integral just becomes L, and we would get that this closed loop line integral, which by Amperes law is mu naught I through, must just be equal to B times L. So the last thing we need to do is to think about what is I through. And if we look at our picture, the current through our loop, there's this loop and this loop and this loop and this loop and this loop. Those all carry the same current I. And so now there's n of those loops that are passing through our n current loops that pass through our red square Amperian loop, we were calling them. So if we have n current loops, each of current I passing through the Amperian loop, which is that red rectangle we drew, then I through, which is just the total current through the Amperian loop, is going to be equal to n times I. All right, so we replace I through with n times I, and our Amperes law becomes mu naught n times I is equal to B times L, or B is equal to mu naught n over L times I. So if we think about this n over L, that's the number of turns per unit length in our solenoid. This is the number of turns per unit length in this coil of wire of wire coil, let's say. Number of turns per unit length of our wire coil. Usually, people denote n over L as little n. This is the turn density, the density of coil, the density of loops in our coil. So therefore, for our solenoid, B is equal to mu naught n times I. So that's the magnitude or the strength of the magnetic field. And you would always use a right-hand rule to tell you the direction. So this is the magnetic field inside the solenoid. It's worth noticing something. There's nothing in this expression that tells you, that has anything to do with the position inside the solenoid. It doesn't say we have to be at the center or at one edge or anything like that. And in fact, if you look at the picture that we drew, we chose a loop where we didn't specify where we were inside the solenoid. We're not at the center, we're not at the edge, we're at some arbitrary distance away from, say, the bottom currents in our cross-section. So this expression for B is independent of the position within the solenoid. The only requirement is that we're actually inside, right? We can't be outside of the solenoid. So the conclusion, therefore, is that, therefore, the magnetic field, B, is uniform within the solenoid. That's really convenient because now we have a very easy way to create uniform magnetic fields. If you wanted to do some kind of experiment inside of a uniform magnetic field, that's really easy to set up. You just take a tube, you wrap a dense coil of wire around that tube, and you pass a current through your wire, a constant current, and all of a sudden you got now a uniform, a constant magnetic field, and you can do whatever experiment that you want to do. And so what we'll find in, probably the next video, in fact, is that we'll start to calculate the force that a magnetic field exerts on a moving charge. And so if you wanted to do some experiment on some distribution of moving charges in a magnetic field, you have a way to set up, if you want, a uniform magnetic field. It's worth just thinking about the comparison of a capacitor and a solenoid. So let's recall capacitors. So with a capacitor, what we did is we said, let's take two conducting sheets, and we'll put opposite charge on those sheets. And so we'll say this is plus Q, and over here we have minus Q. And what we found is that we got a uniform electric field. So capacitors can be used to create uniform electric fields with E equal 0 outside the plates. Right, and so over here we have E equals 0, and over here we have E equals 0. And so now what we have is a solenoid where we can take a coil of wire, and I'm drawing it as a loose coil of wire, but usually what you would do is you'd wind your coil very tightly. Why would you do that? Because then your number of turns per unit length, little n, becomes large, and the magnetic field, which is B inside is equal to mu naught n times I, becomes large. So if you want to make a strong magnetic field, what you would do is you'd make your density of coils as large as possible. So here, what we're going to end up with is a magnetic field that's uniform inside and a magnetic field that's approximately 0 outside. So this is some B inside, and this is B equals 0 outside. Okay, good. So let's do one more thing. Let's imagine that we take our solenoid. So we're gonna do toroid. So what is a toroid? So let's make a really long solenoid, okay? So we make a really long solenoid, and we wrap our wire around the thing. And we pass a current through there. So to make a toroid, we take the two ends of a solenoid and we wrap them around until they connect. Okay, so in other words, we grab the two ends and we're going to bend this thing into a circle until, so we'll take this end and we'll bend it around this way, and we'll take this end and we'll bend it around this way, and we'll form a closed circle. So if we draw it, what we'll do is we'll take, it's like a donut. So we take a donut and then we take our wire and we wrap it around our donut former. Okay, and then somewhere in there we have a battery so that we can run a current through this thing. Okay. And so maybe what we've got is current going in this direction on top of it, and then underneath, which we can't see, the current is going in the opposite direction. Okay, now if you think about this, our solenoid started with no magnetic field outside, and then we wrapped it around and closed it in on itself. And so what we would think then is that we should still guess that outside here, we should still have B equals 0. And just what happens inside is, so let's see if I can get the current direction right. So by the right-hand rule, we wrap our fingers in the current direction around our donut, so they're above the donut on top. We should get magnetic field lines that are going around in this circular direction. And so we have magnetic field that loops around like this. Okay, you could also try to do a bit of a symmetry argument where, again, you imagine all of these as individual current loops. You draw dipole magnetic fields for each of those loops, and what you should find is that you could convince yourself that the magnetic field is 0 outside of the toroid, but non-zero inside. Okay, so let's see if we can apply Amperes Law. So we need to do the line integral of B dot ds around a closed loop, and that's mu naught times I through. Okay, the closed loop that we're going to pick is, in order to make the evaluation of this dot product simple, let's pick a loop that follows the direction of the magnetic field. So this is a loop that's inside our torus, and it's just a circular loop. And we're going to make it parallel to the magnetic field so that when we evaluate B dot ds, our ds vectors are going to be always parallel to the magnetic field. So B and ds are parallel, therefore B dot ds is equal to B ds. So therefore we have the integral of B ds around our closed loop is equal to mu naught I through. Okay, but if we follow a magnetic field line around this loop, then B would be constant everywhere on that loop, and so we end up with B ds around a closed loop is equal to mu naught I through. Okay, so to go further, what we need to do is we need to specify the radius of our loop, And so let's say our loop has radius r measured from the center of the torus, or toroid. And if that's the case, then around the loop is just a circumference of a circle, so that's 2 pi r. And therefore, what we have is 2 pi r times b equals mu naught I through. And then just like the case of the solenoid, what we have is every time our wire loops around the torus, a current I passes through our red Amperian loop. And so if we have n of these turns of wire, so if we have n loops of wire in the toroid, then I through would be equal to n times I. So then we get 2 pi rb is equal to mu naught n times I for I through, or b is equal to mu naught ni over 2 pi r. So this is the magnitude of the magnetic field inside a toroid. Unlike the solenoid, this depends on a position inside the toroid. Note that B depends on the distance r from the center of the toroid. So if we draw a toroid, let me draw one that, like a fat donut, okay? So this is a fat donut. And then we loop our wire around here. And I'm drawing just a few loops, but what we would do is we try to wrap that as tight as possible. Okay, and so let's pick a current direction. Let's just be consistent with what we used over here. So current is pointing in on the top. And so what should happen is we should get a clockwise magnetic field, right? And so, yeah, that's what we drew last time too. Good. And so B is proportional to 1 over r. So that means when r is large, B is small. Okay, so if we draw magnetic field lines here, what should happen is the strength of the field should get weaker as we move further away. That means the density of field lines should decrease, so the spacing between these field lines gets larger and larger. And I didn't draw a perfect torus, but what we should have is over here we should have a really high density of magnetic field lines. So let me insert one here. And so these are clockwise magnetic fields, and so out at this edge where we have a small radius, we have B is large. And then out here where we have a large radius, B is smaller. Okay, and so the solenoid makes a uniform magnetic field. The toroid is similar in the sense that the B is equal to 0 outside, but B is not 0 inside. However, that inside magnetic field is not uniform. It gets weaker as you move further from the center. All right, great. So thanks very much. We're done, I think, what we're going to do about trying to calculate magnetic fields caused by different arrangements of current. We've talked about, I guess, the long straight wire. In fact, we did a finite length of wire as well. We talked about a current loop, which made a dipole type magnetic field. And now we've used Amperes Law to do the solenoid and the toroid. The next topic is to investigate how magnetic fields can exert forces on a moving charge. And so that's what we'll start next time. Thanks very much.